Hello there, and a truly warm welcome to the Sleep Enigma, your quiet corner of the cosmos, a tranquil haven where the vastness of scientific curiosity gently meets the calm of inner peace, and the profound wonders of the universe softly rock you into a restful slumber. Before we embark on this truly grand and immersive celestial journey tonight, I'm genuinely, wonderfully curious. Wherever you are in this incredible world, what time is it for you right now? The stars will soon begin to prick the velvet twilight. Are the first stars beginning to appear where you are? Or is the golden sun just greeting your horizon, promising a new day? Please share a quick note in the comments below. I am always utterly amazed and deeply moved by how many of us are drifting together, connected by this shared moment of contemplation from so many different and beautiful corners of our blue marble. And if tonight's cosmic voyage resonates deeply with you, if it brings a profound sense of wonder and a touch of peace to your soul, please consider extending a gentle like to this video. Perhaps even take a moment to subscribe to the channel so you don't miss any of our future stargazing sessions. Every gentle click, every quiet subscribe, helps more sleepy minds find their way to this serene cosmic haven, expanding our little community of quiet explorers across the globe. Tonight's story is one of truly profound beauty, an epic, sprawling narrative woven from the very first threads of existence, from the fundamental fabric of reality itself. How galaxies, those magnificent luminous cities, those swirling majestic islands of billions upon billions of stars, are born from the deepest, most primordial darkness and the most ethereal, fleeting cosmic dust. My sincere, earnest hope is that this tale won't be so utterly captivating that it keeps you wide awake, your mind buzzing with the thrill of cosmic revelations. But if by some delightful chance it does, well, then at least you'll awaken knowing a little more about the universe's incredible, awe-inspiring infancy, perhaps even before your morning coffee begins to brew its comforting aroma. So now, truly, gently, settle in. Let every muscle in your shoulders softly drop. Release any lingering tension and allow your breath to deepen and slow, becoming a gentle, rhythmic tide, mirroring the cosmic flow. You are about to drift effortlessly, carried by the current of thought and wonder through an unimaginable 13.8 billion years of cosmic history. There is absolutely no rush here. The stars, in their infinite, silent patience, will wait for you. Let us gently begin. The universe's infancy, a primeval swirl of limitless potential. Close your eyes for a moment, if you like, and really try to summon an image, a fleeting impression of the universe as it was, a staggering 13.8 billion years ago. Forget everything you know about empty space, about stars and planets, about vast distances, about time itself in the way we usually perceive it. Imagine instead an existence that was unimaginably compact, a state of pure, concentrated energy and limitless potential, utterly defying our everyday concepts of space, time, and size. It wasn't merely small, it was, in theoretical terms, a quantum singularity, a point of infinite density and temperature, where all the known laws of physics as we currently understand them break down. Imagine something hotter than the very core of any star you can possibly conceive of, a temperature so extreme it would vaporize thought itself, a primordial crucible of creation where familiar laws of physics simply did not apply in the same way, and denser than the most packed, most groundbreaking calendar of a brilliant physicist during Nobel Prize season, crammed with world-altering discoveries and paradigm shifts. It was a universe contained within an infinitesimal speck, a seed of everything to come, brimming with potential. The Big Bang, more than an explosion, an expansion of space, and then, in a singular, defining, utterly momentous event that continues to challenge our fullest human comprehension, it began. It wasn't an explosion in the violent, destructive sense we typically imagine fireworks or bombs shattering into a pre-existing void. That analogy is misleading because it implies there was an outside for the universe to explode into. No, the Big Bang was more akin to an incredibly rapid, astonishingly graceful swelling, an inflation of space itself. Crucially, it wasn't an expansion into existing space, but rather an expansion of space itself, creating new space as it went. This expansion occurred in every conceivable direction, not just quickly, but at a rate faster than the speed of light, driven by a hypothetical energy field called the inflaton field. This superluminal expansion doesn't violate Einstein's theory of relativity because it's space itself that's expanding, not objects moving through space. Picture, if you can, a balloon being inflated, not gently with a slow breath, but with a mighty, instantaneous burst of air from a leaf blower set unequivocally to cosmic. There wasn't debris flying through some pre-existing empty space. In a mind-bending twist of reality, space was the debris, and it was literally making itself, stretching and unfolding into existence, moment by astonishing moment, carrying the nascent universe along for the ride, from something smaller than an atom, 10-20 meters, to something the size of a grapefruit, around 10 centimeters, to, in the briefest fraction of a second, between 10:36 and 10:32 seconds after the initial singularity. This inflationary period smoothed out any initial irregularities and set the stage for the homogeneous and isotropic universe we observe today, while also generating the quantum fluctuations that would later become the seeds of structure. The exact nature of the inflaton field and the precise mechanism of inflation remain areas of active research, but the observable consequences, like the extreme smoothness of the cosmic microwave background and the flatness of the universe, provide compelling evidence for it. The primordial soup, fundamental forces and particles emerge. In those first fleeting, almost imperceptible microseconds following inflation, the very earliest moments from 10 to 32 seconds to about 10-6 seconds, truly a blink beyond all human comprehension, shorter than the time it takes light to cross a single room. The nascent universe was a seething, turbulent, incredibly energetic broth of fundamental particles. It was a quark-gluon plasma, a state of matter so hot, temperatures upwards of 1032 Kelvin initially, cooling rapidly, and dense that quarks and gluons could not yet be confined within protons and neutrons. This primordial plasma existed at energies so high that physicists can only replicate them in the most powerful particle accelerators for the briefest moments. Quarks, the minuscule building blocks of all matter, up, down, charm, strange, top and bottom, each possessing a fractional electric charge and a color charge, jostled playfully and furiously with gluons, the invisible, powerful force-carrying particles that bind them together, mediating the strong nuclear force, the strongest of the four fundamental forces responsible for holding atomic nuclei together, with a range of only about 10-15 meters, the size of a nucleus. Leptons such as electrons, muons, taus and their associated neutrinos, electron neutrinos, muon neutrinos and tau neutrinos, which interact via the weak nuclear force and gravity, also zipped through this primordial soup, constantly interacting with each other and with quarks. Photons, shimmering packets of pure light and energy, zipped around like restless toddlers after far too much sugar, unable to settle into any stable pattern, constantly scattering off free electrons and other charged particles. This constant scattering meant the universe was entirely opaque, like a dense luminous fog, similar to the interior of a star, where light cannot travel freely without being scattered or absorbed. And all the while, amidst this primal subatomic dance, gravity, one of the four fundamental forces of nature, along with the strong, weak and electromagnetic forces, ever the patient, ever-present and persistent sculptor, quietly began to take its first meticulous notes. Its subtle, long-range influence wove through the chaos, observing the earliest, most fundamental interactions, already beginning to shape the future on the largest scales, even as the other forces were still distinguishing themselves from a hypothesized grand unified force at even earlier, more energetic times. It was a scene of unparalleled chaos, blindingly hot, dazzlingly bright beyond our visual spectrum, and let's be honest, profoundly uncomfortable. Certainly not a place conducive to serene stargazing or leisurely marshmallow roasting just yet. But this early universe, for all its tumultuous mayhem, for all its fiery intensity, was absolutely brimming with the most incredible potential, a primordial soup from which everything, literally everything, would eventually emerge. From quarks to atoms, the first building blocks, As the universe continued its rapid expansion, it also continued to cool. About 10 to 6 seconds, 1 microsecond, after the Big Bang, the temperature dropped sufficiently to about 10 to 12 Kelvin for the strong force to effectively bind quarks together into more stable composite particles called hadrons. This process is known as hadronization. The most common hadrons formed were protons, made of 2 up quarks and 1 down quark, and neutrons, made of 1 up quark and 2 down quarks. At this stage, the universe was still dominated by radiation, and a dense plasma of these newly formed protons, neutrons, and electrons. The universe was still too hot for atomic nuclei to form. Then, about 1 second after the Big Bang, the temperature dropped further to approximately 1 billion Kelvin, 119 K. This cooling was crucial because it allowed for the process of Big Bang nucleosynthesis, BBN, to begin, lasting for only a few minutes. This brief but vital period of nuclear fusion saw protons and neutrons combine to form the nuclei of the simplest elements. The conditions were just right, hot enough for fusion but cool enough for the newly formed nuclei to avoid being immediately blasted apart. The vast majority of baryonic matter, ordinary matter, created during BBN was hydrogen, a single proton making up about 75% of the baryonic mass of the universe, and helium, 2 protons and 2 neutrons, mostly helium-4, making up about 25% by mass, with trace amounts of helium-3 and deuterium. A tiny trace amount of lithium-7 and beryllium-7 was also formed, but heavier elements could not be created in significant amounts due to the rapidly dropping temperature and density, and the lack of stable nuclei with atomic mass 5 or 8, the mass gaps that prevent a simple path to heavier elements via successive addition of single nucleons. These humble atoms, the very first, the true ancestors of all matter, would eventually go on to build everything we know. The majestic stars that glitter above us, the planets that tirelessly orbit them, the very people contemplating the cosmos. At this moment, even the pet lizards quietly observing their terrariums with ancient reptilian wisdom, and of course the magnificent, awe-inspiring structures we call galaxies. The universe at this point was still a hot, dense plasma of these newly formed nuclei and free electrons, still completely opaque to light because photons could not travel far without constantly scattering off the abundant free electrons. This meant the universe remained a blinding fog of light. The predictions of BBN regarding the primordial abundances of light elements are in excellent agreement with observations of the oldest, most pristine gas clouds in the universe, providing strong confirmation of this early cosmic event. The unveiling. When light broke free and the cosmic dark ages began now, let's fast forward through the immense yet relatively brief in cosmic terms expanse of time. Roughly 380,000 years after that initial cosmic swell of the Big Bang, a truly profound and exquisitely beautiful event occurred. The universe, having expanded and cooled significantly since Big Bang nucleosynthesis, reached a critical temperature of about 3,000 Kelvin, approximately 2,700 degrees Celsius or 4,900 degrees Fahrenheit. At this temperature, the free-floating protons and electrons, previously too energetic to bind into stable atoms, finally slowed down enough. The electromagnetic force could now overcome their kinetic energy, allowing them to settle and capture each other, forming the first stable, electrically neutral hydrogen atoms and helium atoms. Recombination and decoupling, the universe becomes transparent. This profound liberation of light, this cosmic unveiling, is a moment known to astronomers as recombination, though technically it was more of a combination for the first time, as they hadn't been combined before. It's also sometimes referred to, more accurately, as decoupling, because photons decoupled from matter. Up until this point, the universe was a dense ionized plasma, and photons were constantly scattering off free electrons, preventing them from traveling far, a photon-electron fluid that made the universe opaque. Imagine trying to see through a dense fog, where light bounces off every water droplet. This was the universe before decoupling. But once electrons were bound into neutral atoms, the universe's fog lifted, becoming transparent. Photons were suddenly free to travel unimpeded, radiating outwards into the newly transparent cosmos. This event created what we now call the cosmic microwave background, CMB. Think of the CMB as the soft, omnipresent, lingering afterglow of the Big Bang itself, a faint, ancient hum of energy that still permeates and echoes throughout the entirety of the universe today. It's like a fossilized echo, the oldest light we can possibly detect, a direct snapshot of the universe in its infancy, radiating from every direction in space. If our limited human eyes possessed the remarkable ability to see microwaves, which is the wavelength this ancient light has been stretched into by the universe's ongoing expansion, peaking at about 1.9 million meters corresponding to a temperature of 2.725 Kelvin, the entire night sky, rather than being dark with countless pinpricks of stellar light, would instead glow with a gentle, diffused, uniform warmth, a faint reddish orange of that ancient fire, radiating from every single direction, a soft, ethereal, all-encompassing light. The tiny temperature variations in the CMB, measured to be incredibly precise, only about 1 part in 100,000 or micro-Kelvin fluctuations, are crucially important. These minute variations represent the slight differences in density in the early universe, the very seeds of all future structure. These primordial density fluctuations, originating from quantum jitters during the inflationary epoch, are the gravitational blueprints for everything that followed, including the vast cosmic web. These anisotropies, temperature differences in the CMB, are the most robust observational evidence supporting the Big Bang theory and the inflationary model, and their statistical properties match predictions from the lambda CDM, lambda cold, dark matter cosmological model with astonishing accuracy. Satellite missions like COBE, WMAP, and Planck have mapped these tiny fluctuations with increasing precision, providing a baby picture of the universe that reveals its fundamental properties. The cosmic dark ages, a period of gravitational assembly saved. Despite this newfound diffuse glow, there were still no individual distinct stars, no fully formed galaxies as we know them, not yet. The universe at this point was still primarily a dark, vast and steadily expanding cloud of diffuse gas, predominantly neutral hydrogen and helium, brimming with immeasurable potential. If you could have floated, utterly disembodied, free from any physical form through this primordial expanse, you would have seen nothing but the most subtle, almost imperceptible ripples, tiny, minuscule irregularities in the otherwise incredibly smooth, uniform distribution of matter. These ripples, however, were absolutely everything. They were the faint, gravitational whispers of quantum fluctuations from the absolute earliest moments of existence, microscopic quantum uncertainties stretched and amplified across the vastness of the cosmos by the rapid initial expansion of inflation. Some regions, by pure chance, were just ever so slightly denser than others, barely a measurable difference to our modern instruments, really. But gravity, with its relentless, unwavering and democratic pull, noticed. And gravity, once it notices, does not and cannot forget. Its influence, though initially subtle, would be absolute and inexorable over cosmic timescales, patiently drawing matter together over unimaginable stretches of time measured in hundreds of millions of years. These infinitesimally denser pockets of hydrogen and helium began their slow, inevitable dance, pulling in more and more material from their surroundings. Slowly, gently, patiently they gathered, much like cosmic dew forming delicate, shimmering droplets on an invisible spiderweb spun across the burgeoning cosmos. These nascent clumps, the very seeds of what would one day become future galaxies, were utterly invisible to any naked eye, had such eyes even existed then. Yet they were already diligently, patiently setting the grand stage for all the dazzling, intricate drama of cosmic evolution that was yet to unfold. This period, spanning from about 380,000 years to roughly 400 million years after the Big C. Bang is known as the cosmic dark ages. It wasn't dark due to an absence of matter, but because there was no luminous matter. There were no stars yet, no galaxies, no quasars, just a vast expanding sea of transparent, neutral gas. The universe was indeed quiet, except for the fading glow of the CMB. The average temperature of the gas dropped from 3000 Kelvin at recombination to a mere tens of Kelvin, making it too cold to emit significant amounts of light, like from blackbody, radiation in the visible spectrum, and too diffuse for efficient star formation. It was a time of deep, pregnant stillness before the glorious storm of creation, a long collective breath in before the universe finally exhaled its first brilliant starlight. And yet, even now, with all our powerful telescopes, our complex supercomputer simulations, and our intricate equations, we are still meticulously, passionately piecing together how it all unfolded. How did these minute, almost negligible fluctuations eventually lead to the sprawling grandeur of majestic spiral galaxies or the ancient, serene ellipticals? Why did some parts of the universe become bustling, vibrant hubs of stars, teeming with activity, while others remained vast, dark, and seemingly empty voids, the silent stretches between? The answers, we profoundly believe, are intricately written across the cosmos itself, visible in every glowing nebula, etched within every ancient star cluster, and revealed in the subtle patterns of the CMB. We just have to keep listening, keep observing with ever more sophisticated tools, and keep learning with open minds. The Cosmic Dark Ages. The invisible architect, dark matter and dark energy. Within this pervasive darkness, a silent, invisible force was orchestrating the future. Dark matter. Its existence is one of the most significant mysteries in modern astrophysics, yet we have compelling evidence for it through its profound gravitational effects. Dark matter is estimated to constitute about 27% of the total mass energy of the universe, with ordinary baryonic matter, protons, neutrons, electrons making up only about 5%. It doesn't emit, absorb, or reflect light, hence dark. Nor does it interact significantly with ordinary matter other than through gravity, making it incredibly difficult to detect directly. This means it doesn't experience the same pressure, forces, or cooling mechanisms that ordinary gas does, allowing it to collapse into structures much earlier and more efficiently. Alongside dark matter, another enigmatic component, dark energy, plays a pivotal role, though its influence becomes dominant later in cosmic history. Dark energy is believed to be a form of energy that permeates all of space and tends to accelerate the expansion of the universe. It currently makes up about 68% of the total mass energy density of the universe. While its effects were minor during the initial collapse phase of galaxy formation, its growing dominance in recent cosmic epochs, roughly the last 5 billion years, means it acts as a cosmic anti-gravity, pushing galaxies and clusters apart, preventing some structures from forming and stretching the existing cosmic web, which we'll discuss further. The cosmic web, dark matter's scaffolding. During the Dark Ages, the invisible gravitational pull of clumps of dark matter began to draw in the ordinary matter, the hydrogen and helium gas. These dark matter clumps formed much earlier than baryonic structures because they were not subject to the pressure oscillations, baryon acoustic oscillations, that affected ordinary matter before recombination. This early formation of dark matter over densities provided the essential gravitational scaffolding upon which all later luminous structures would be built. Imagine the universe like a vast, intricate three-dimensional spiderweb of cosmic proportions spun from invisible threads. This is the cosmic web, the largest known structure in the universe. These threads are the filaments of dark matter and ordinary gas stretching across billions of light years. Dense knots, where these invisible filaments of dark matter intersected, became the primary hubs, the cities and superclusters of the universe, regions where galaxies would ultimately cluster together, much like seeds finding the richest, most fertile soil to germinate and thrive. These knots contain vast numbers of galaxies, often bound together into galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, along with vast amounts of hot X-ray emitting gas and dark matter. Long ethereal tendrils or filaments stretched between these hubs, acting as gravitational highways, pulling galaxies along invisible rails of gravity, guiding their cosmic dance, funneling gas and smaller galaxies towards the denser regions where they would interact and merge, and the empty spaces, the vast echoing expanses in between these intricate threads. Those are the voids, truly immense, eerie, and profoundly silent stretches of near nothingness, where few, if any, stars or galaxies will ever manage to form, representing the coldest, emptiest, most desolate places in the cosmos, a stark testament to the uneven distribution of matter on the largest scales. This cosmic web is not just a static map, it's a dynamic structure that continues to evolve, with galaxies constantly flowing along its gravitational currents, influenced by the expansion of the universe and the ongoing pull of gravity. The cosmic web provides the environment that dictates a galaxy's fate, whether it will undergo frequent mergers, experience steady gas accretion, or become isolated in a void. Understanding the evolution of this cosmic web is a central goal of modern cosmology, probed by large-scale surveys of galaxies and the intergalactic medium, gravitational collapse and the intergalactic medium, IGM. It was in these dense intersections and filaments of the cosmic web that proto-galaxies had the most to gain, given the abundance of resources, vast reservoirs of gas and smaller galaxy precursors, and paradoxically the most to fear, due to the high likelihood of energetic interactions and collisions. Within these deep gravitational wells, the hydrogen and helium gas, what we call the intergalactic medium or IGM, began to collapse under its own weight. As the gas was pulled inward by gravity, it lost potential energy, which was converted into kinetic energy, causing its temperature to rise significantly, forming shock waves as it crashed into pre-existing gas. This IGM is far from truly empty space. It's the vast diffuse network of gas that permeates the universe between galaxies and galaxy clusters. It acts as the universe's cosmic lunchbox, providing the raw ingredients for galaxy formation. While incredibly tenuous, averaging just a few atoms per cubic meter, it represents the vast majority of baryonic matter in the universe. Galaxies can grow by accreting this gas from the surrounding IGM, especially through cold accretion streams that penetrate the hot halos of dark matter. This gas cools as it falls into the gravitational potential wells, eventually reaching densities and temperatures sufficient to form stars. But this process was incredibly slow. The gas had to fall into incredibly deep pockets, compacting under its own immense gravitational pull, until the temperatures within these nascent cores rose to millions of degrees Celsius. Only then, at these extreme temperatures and pressures, could nuclear fusion begin. That incredible, intricate nuclear dance where lighter atomic nuclei combine to form heavier ones, e.g. hydrogen to helium, releasing the vast, unimaginable amounts of energy that light up a star and make it shine with such fierce brilliance, a process governed by Einstein's famous equation EMC2. But the early universe, in its deep, unfolding wisdom, wasn't in any rush. It allowed gravity to work at its own unhurried, relentless pace, gently coaxing the diffuse gas into denser and denser clouds. Slowly, patiently, these immense clouds collapsed under their own inexorable weight. And somewhere, deep within one of those particularly dense knots of matter, amidst the cosmic silence, the very first spark would finally ignite, a single, brilliant point of light in an otherwise boundless ocean of dark. And when that happened, truly, everything changed. The universe was forever altered. But here, during this long, silent interlude, this profound cosmic pause, the universe was still gathering its breath, like an immense orchestra meticulously tuning each instrument, each individual string, each pipe, before the very first soaring, breathtaking note. The fundamental elements were perfectly in place. The cosmic stage was set, but the grand, symphonic music of the galaxies had yet to begin. No galaxies, no stars, just a slowly growing tension, a palpable sense that something unimaginably beautiful, something utterly transformative was about to happen. The light eventually was coming, and it would be glorious. The dawn of starlight, the first beacons ignite the void. Then, after hundreds of millions of years of patient gravitational collapse, roughly 200 to 400 million years after the Big Bang, a pivotal moment arrived. Somewhere deep within one of those collapsing clouds of primordial hydrogen and helium, gravity tightened its relentless, unyielding grip to an extreme degree. At the very center of that dense, invisible swirl of gas, pressure soared to unimaginable levels, reaching a critical threshold. Temperatures climbed rapidly, reaching millions of degrees Celsius. Atoms, squeezed beyond anything we encounter on Earth, were pushed so incredibly close together that their very fundamental nature began to change, began to interact in a new, profound way. Their nuclei began to fuse. Hydrogen nuclei slammed together to form helium, releasing an enormous amount of energy in the process. And in that singular, momentous occasion, almost certainly unnoticed by any conceivable observer in the vast, empty cosmos, utterly unceremonious in its solitary inception within the void, a star was truly born. It was the very first, brilliant, self-sustaining light source since the Big Bang itself, a beacon cutting through the cosmic night, igniting an entirely new era. Population 3. Stars, the primordial giants and their fates. These were no ordinary stars. They were a special primordial breed, so distinct from what we see today that astronomers call them Population 3 stars. They were utterly unlike anything we observe in the universe now. Their formation conditions were unique. They formed in the purest environment the universe has ever known, a pristine, almost sterile medium, consisting solely of hydrogen, about 75%, helium, about 25%, and trace lithium, a tiny fraction of a percent, all direct remnants from the Big Bang nuclear synthesis. This pristine composition, this absolute lack of heavier elements, which astronomers refer to as metals, meaning any element heavier than helium, fundamentally changed their physics. Without heavier elements, which act as coolants by efficiently radiating away heat through various emission lines, like fine structure lines from carbon and oxygen ions, allowing dense gas clouds to shed thermal energy and contract. The primordial gas clouds struggled to cool efficiently and fragment into smaller pieces. This meant that the gas had to collapse to much higher densities and temperatures before it could fragment and form stars. Consequently, these stars had to be incredibly massive, often hundreds or even thousands of times more massive than our own Sun, with masses estimated between 100 to 1,000 solar masses, though some theoretical models suggest even larger, up to 105 solar masses for the very first ones, forming in mini-halos of dark matter, with masses of about 106 solar masses. This extreme mass also caused them to burn far hotter. Surface temperatures could exceed 100,000 Kelvin. Far brighter, millions of times brighter than the Sun with luminosities up to 106 L, and far faster than the stars we are familiar with today. Some of these titans may have lived for only a few million years, a mere blink in cosmic timescales considering our Sun will live for 10 billion years before reaching their dramatic end. Their deaths were equally spectacular and profoundly impactful on the early universe. The most massive Population 3 stars, those between 140 and 260 solar masses, are thought to have ended their lives in pair instability supernovae. In these events, the star's core becomes so incredibly hot that gamma-ray photons transform into electron-positron pairs. This reduces the internal radiation pressure that supports the star against gravitational collapse, leading to a catastrophic, runaway implosion. The subsequent explosion is so powerful that it completely obliterates the star, scattering all its material, including newly synthesized heavy elements, into space without leaving a compact remnant like a neutron star or a black hole. Other, even larger Population 3 stars, perhaps exceeding 260 solar masses, or those formed via direct collapse, might have bypassed the supernova stage entirely and collapsed directly into supermassive black holes, a process known as direct collapse. These direct collapse black holes are one leading theory for the existence of very massive black holes, up to 105 or 106 solar masses, so early in the universe's history, at redshift 6.6, providing the seeds for the quasars we observe at high redshifts. Understanding the initial mass function and remnants of Population 3 stars is a critical area of research, as they are key to understanding the early chemical enrichment and black hole population of the universe. And just to be clear, if you were somehow floating nearby, even at a safe cosmic distance, let's be honest, you'd be very, very crispy, likely vaporized instantly by their raw energy output, powerful stellar winds, and potentially powerful gamma-ray bursts associated with their deaths. Cosmic rionization. Light dispels the darkness. If you could have witnessed this breathtaking era, roughly 200 to 400 million years after the Big Bang, you would have seen these first stars lighting up their surroundings like immense, fiercely burning bonfires flickering in a vast primordial cosmic forest, each a solitary beacon, slowly multiplying across the dark expanse. One by one, their searing, powerful ultraviolet light began to pierce the ancient pervasive fog of neutral hydrogen that had enveloped the universe since its earliest moments. Slowly, gradually, but inexorably, the profound darkness that had reigned for so long began its slow, majestic retreat. This transformative period is known to astronomers as cosmic rionization. The intense ultraviolet UV radiation streaming from those newborn population 3 stars and early proto-galaxies possessed enough energy, photons with energy greater than 13.6 eV, the ionization potential of hydrogen, to strip electrons from the surrounding neutral hydrogen and helium atoms, essentially ionizing them, and making the intergalactic medium, the space between galaxies, transparent to light once more. This process was not instantaneous or uniform across the universe. It was a patchy, gradual affair, with bubbles of ionized hydrogen expanding outward from these early luminous sources. These bubbles grew, merged, and overlapped over hundreds of millions of years, eventually rionizing the vast majority of the intergalactic medium by about 1 billion years after the Big Bang, at a redshift of approximately Z6. It was as though someone had finally cracked open the massive cosmic shutters of a vast greenhouse, allowing the brilliant illuminating light to flood in and reveal everything within its boundless interior. Rionization marked the end of the cosmic dark ages and set the stage for the formation of the complex structures we see today. The timeline and exact sources of rionization are still under intense investigation, with both early galaxies and quasars, powered by active supermassive black holes, thought to contribute. Observing the rionization epoch is a key science goal for JWST and future 21 cm radio telescopes. The legacy of the first stars, stellar feedback and chemical enrichment, from our distant vantage point, billions of years later, we cannot see these first stars directly with our current technology. They were simply too brief in their existence, too distant, and their light by now is far too faint and stretched by cosmic expansion, massively redshifted into the infrared spectrum, sometimes by a factor of 10, 20 or more, making them challenging to detect individually. However, their indelible fingerprints, their profound legacy are everywhere. Woven into the very fabric of the cosmos, they fundamentally transformed the universe from a cold and dark expanse into a warm and glowing one. Crucially, they seeded the cosmos with the very first heavy elements, astronomers' term for anything heavier than hydrogen and helium, such as carbon, oxygen, nitrogen, iron, silicon, and even trace amounts of heavier elements like gold and uranium. These elements, forged in the fiery cores through nuclear fusion processes like the CNO cycle, and then dramatically blasted into space by the powerful supernova explosions of population 3 stars, are the essential building blocks of everything, more complicated than hydrogen and helium. This includes rocky planets like Earth, complex organic molecules, water, the very components of life as we know it, you, me, and perhaps that soothing cup of tea you might be quietly sipping right now. In a profound and beautiful way, these pioneering stars were the universe's first true artists, sketching the initial rough outlines of what would eventually become galaxies on the vast blank canvas of primordial space. This process of stellar feedback, where stars influence their environment, is critical. Powerful stellar winds from massive young stars and the subsequent supernova explosions inject tremendous amounts of energy and momentum into the surrounding gas. This energy can ionize and heat gas, As discussed with ionization, disperse. Gas, drive out gas from small halos, preventing further star formation, negative feedback. This is particularly important in small early galaxies, helping to explain why dwarf galaxies are less efficient at forming stars than larger ones. Trigger star formation. In some cases, the shock waves from supernovae can compress nearby gas. Clouds paradoxically triggering new star formation, positive feedback. Enrich the interstellar medium, ISM. Distribute the newly synthesized heavy elements throughout the gas clouds from which future generations of stars will form. And so the great cosmic cycle truly began. Gravity continuously pulls in fresh gas from the vast intergalactic medium, the space between galaxies. New stars are born within its dense embrace. They shine with fierce brilliance, live their often brief lives and then die, scattering their precious, newly forged, enriched contents back into the surrounding medium through powerful stellar winds and supernova explosions. This recycling process allows for even more stars to form, each subsequent generation building upon the ashes and legacy of the last, layering complexity upon complexity like stardust sediment accumulating over eons. You might find yourself wondering, how do we know all this happened if we've never actually seen these ancient first stars, these population 3 giants? The answer is hidden in the subtle patterns of light, the precise chemical compositions of the oldest visible stars, and the faint ubiquitous glow of the cosmic microwave background, like ghostly fingerprints left on the cosmic windowpane. By meticulously studying the oldest observable galaxies, which are seen at high redshift, meaning their light originated when the universe was very young, up to a redshift of Z15, implying observation of galaxies when the universe was only 250–300 million years old. By analyzing the chemical signatures within ancient stars in our own galaxy, like those found in globular clusters in the Milky Way's halo, which are extremely metal-poor, suggesting they formed from gas enriched by only 1 or 2 previous generations of stars, and by precisely measuring the faint, incredibly uniform glow of the cosmic microwave background, looking at its tiny temperature fluctuations which encode information about the early universe's composition and structure. Astronomers can painstakingly piece together the universe's incredible childhood story in astonishing detail. It's a bit like reconstructing the entire history of a vast ancient forest by carefully examining its oldest trees, analyzing the composition of its soil, and even studying the prevailing direction of the ancient winds. The clues are subtle, yes, but they are undeniably there, waiting patiently to be deciphered by human ingenuity and increasingly powerful instruments. And excitingly, very recently, we've truly begun to catch direct glimpses with groundbreaking telescopes like the James Webb Space Telescope, JWST. Its unparalleled infrared vision allows it to peer back further in time. Due to the extreme redshift of light from the early universe, seeing the extremely redshifted light from these very early objects, which are too faint and distant for visible light, telescopes, we are finally starting to see some of the earliest galaxies taking shape. Small, chaotic, glowing clumps of stars from just a few 100 million years after the Big Bang, essentially witnessing them in their infancy, their nascent, irregular forms. We are quite literally peering into the very nursery, where the first light of structured creation bloomed, witnessing the very dawn of galaxies. It's a humbling and truly awe-inspiring thought, isn't it? These pioneering stars, these cosmic giants, lived and died long before our own solar system was even a fleeting dream in the cosmic mind, before the atoms that would form our sun and planets were even forged and cast into the cosmic recycling bin. Their light embarked on an unimaginable journey across space for billions upon billions of years, past countless colliding galaxies, past silent, wandering black holes, past the slow, majestic growth of our own Milky Way, until finally, it landed softly on the precisely curved mirror of a telescope pointed patiently at the night sky. And now, in this quiet moment, it rests in your mind, in the serene quiet of your evening, as you gently, peacefully drift towards sleep. The universe, once profoundly dark and silent, had finally lit its first brave lanterns. The long primordial night had ended, and the glorious age of galaxies was about to begin. The assembly of galactic cities. Structure emerges from cosmic chaos. The universe was now unmistakably glowing. Not with a brilliant, overwhelming blaze of light from everywhere at once, but more like the first delicate ethereal hint of dawn spreading across a cold, silent morning. The stars had unequivocally arrived, their light unraveling the pervasive fog that had long obscured the cosmos, warming the profound silence that had reigned for eons. But they were, for the most part, still scattered, isolated, flickering across the immense dark-like solitary distant campfires in a vast empty wilderness. There were no cities yet, no grand cosmic roads connecting them, just lonely pockets of light suspended in the vast expanding void. Hierarchical formation, building blocks of galaxies. But gravity, that tireless architect of the cosmos, that universal sculptor, had other grander plans brewing. Those scattered stars weren't just aimlessly floating at random, they were being inexorably drawn together, pulled by invisible gravitational threads, binding them into larger, more cohesive collectives. Everywhere you looked, or would have looked, if you possessed the incredible ability to see in the non-visible ultraviolet spectrum and commanded the profound patience of a truly cosmic being, small clumps of stars and gas, the proto-galaxies, were gradually converging. Gravity was quietly and diligently threading them together, weaving them into larger, more complex structures through a process of hierarchical formation. This model, a cornerstone of modern cosmology and supported by extensive observational evidence and numerical simulations, like the Millennium Simulation, Illustris TNG, and Eagle, suggests that larger structures, like galaxies and galaxy clusters, form from the aggregation of smaller ones over cosmic time. The scattered stellar villages were steadily becoming towns. The towns would eventually grow into bustling cities, and these cities, these primordial nascent proto-galaxies, were the very first drafts, the initial sketches, the rough prototypes of what we now majestically call galaxies. This process primarily occurred within the gravitational influence of dark matter halos, which are the larger invisible envelopes of dark matter that galaxies reside within. These halos grow by accreting smaller halos and diffuse dark matter, and the baryonic matter, gas, then sinks to the center of these halos where it can cool and form stars. The dynamics of early galaxy growth, collisions and mergers. This grand assembly, this cosmic construction, didn't happen neatly, nor was it meticulously planned according to some divine blueprint. There were no precise schematics, no cosmic engineers, marking out perfect spiral arms with rulers and protractors. It was a gloriously messy, chaotic, and profoundly dynamic process, driven by gravity and the complex hydrodynamics of gas. Clumps of stars and gas collided with each other, merged, violently ripped each other apart under immense tidal forces, and then merged again in new, often surprising configurations. The early universe was, in essence, a wild, untamed, rough and tumble neighborhood, a relentless cosmic construction site without a foreman. Immense gas clouds, trillions of times the mass of our sun, crashed head-on into each other, generating powerful shock waves that compressed the gas, stripping away some of its kinetic energy and sparking furious new star formation, sometimes triggering starburst events of unprecedented intensity that consume gas rapidly. Stars were violently flung from one gravitational group into another, like pebbles skipping across a vast still pond. Some of these early galaxies formed incredibly quickly, growing fat on vast reservoirs of nearby gas and voraciously gobbling up their smaller, less massive neighbors in acts of galactic cannibalism. This process, where a larger galaxy accretes or swallows smaller ones, is a common mode of growth for massive galaxies and leads to the buildup of galactic bulges and halos. Others, less fortunate or simply residing in quieter, more isolated regions of the cosmic web, stalled in their growth, stranded in serene, lonely corners of space, much like cosmic wallflowers at a silent, never-ending ball, patiently waiting for a partner that never came. At this initial stage, galaxies certainly didn't resemble the elegant, majestic spirals or the massive, smooth ellipticals we admire in glossy, high-resolution telescope images today. They were irregular, chaotic, unrefined, truly more akin to amorphous space blobs or glittering cosmic smudges than the symmetrical beauties we might instinctively imagine. They lacked the distinct features that characterize mature galaxies, and yet even in their glorious chaos, they were steadily growing, gaining mass, evolving. Slowly, inexorably, their shapes began to stabilize, gently nudged by the omnipresent shaping hand of gravity and intricately sculpted by their dynamic environments, the constant interactions with other clumps, the continuous inflow of fresh gas from the cosmic web, known as cold accretion, where cool gas streams directly into galactic halos, providing fuel for star formation, the powerful stellar winds from young, massive stars, and the feedback from early supermassive black holes lurking at their centers. These black holes, often in an active galactic nucleus (AGN) phase, powered by accreting gas, can either trigger star formation by compressing gas through outward moving shocks, or paradoxically quench it by heating and expelling gas through powerful jets and winds, a critical regulatory mechanism in galaxy evolution that prevents galaxies from growing too large too quickly. This AGN feedback is crucial for explaining the observed properties of massive galaxies, like the lack of very massive, highly star-forming galaxies in the present universe, and the intricate relationship between black hole mass and galaxy properties, e.g. the MS relation. The cosmic web, detailed structure and evolution. Much of this early fundamental architecture was profoundly influenced by an even larger, grander structure that was simultaneously forming, the magnificent cosmic web. This is the largest known structure in the universe, a vast, intricate, three-dimensional lace of luminous matter, meticulously woven across the entire universe, with dark matter providing the invisible scaffolding that guided its formation. The cosmic web is an emergent property of the gravitational collapse of matter in an expanding universe, starting from the small initial density fluctuations from the inflationary epoch. Dense knots, where these invisible filaments of dark matter intersected, became the primary hubs, the cities and superclusters of the universe, regions where galaxies would ultimately cluster together, much like seeds finding the richest, most fertile soil to germinate and thrive. These knots contain vast numbers of galaxies, often bound together into galaxy clusters, the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, along with vast amounts of hot X-ray emitting gas, the intracluster medium, and crucially even more dark matter. Long ethereal tendrils or filaments stretch between these hubs, acting as gravitational highways, pulling galaxies along invisible rails of gravity, guiding their cosmic dance, funneling gas and smaller galaxies towards the denser regions where they would interact and merge. And the empty spaces, the vast echoing expanses in between these intricate threads, those are the voids, truly immense, eerie, and profoundly silent stretches of near nothingness, where few, if any, stars or galaxies will ever manage to form, representing the coldest, emptiest, most desolate places in the cosmos, a stark testament to the uneven distribution of matter on the largest scales. This cosmic web is not just a static map, it's a dynamic structure that continues to evolve, with galaxies constantly flowing along its gravitational currents, influenced by the expansion of the universe and the ongoing pull of gravity and the accelerating influence of dark energy. The cosmic web provides the environment that dictates a galaxy's fate, whether it will undergo frequent mergers, experience steady gas accretion, or become isolated in a void. Understanding the evolution of this cosmic web is a central goal of modern cosmology, probed by large-scale surveys of galaxies and the intergalactic medium. It was in these dense intersections and filaments of the cosmic web that proto-galaxies had the most to gain, given the abundance of resources, vast reservoirs of gas and smaller galaxy precursors, and paradoxically the most to fear, due to the high likelihood of energetic interactions and collisions. When you have a massive amount of gas and a powerful gravitational pull concentrated in one place, things tend to get a little dramatic, a little explosive. Galaxies, like colossal cosmic ships, would inevitably crash into one another. These were not violent, sudden impacts in the way you might expect a car crash to be, where solid objects shatter. Instead, they were slow-motion ballets of gravity, incredibly drawn-out cosmic dances that could unfold over hundreds of millions, even billions of years. The stars themselves being incredibly far apart within their respective galaxies, the distance between stars is vast compared to their size. If the Sun were a grapefruit, the nearest star, Proxima Centauri, would be thousands of miles away, rarely actually hit anything at all. But their immense gravitational fields did tangle and intertwine. Tidal forces, the differential pull of gravity across the large extent of a galaxy, twisted galaxies into strange, distorted shapes, pulling out long, elegant streams of stars and gas that can span hundreds of thousands of light years, forming visible tidal tails and bridges. These tidal tails are telltale signs of recent or ongoing galactic interactions and are often observed in merging systems. And crucially, gas clouds within the colliding galaxies smashed into each other with immense force, converting kinetic energy into thermal energy, compressing violently and sparking furious explosive bursts of new star formation, a phenomenon astronomers romantically refer to as starbursts. These bursts of star formation can temporarily make merging galaxies incredibly bright, often radiating strongly in the infrared spectrum as the dust heats up from newly formed stars. So amid the apparent chaos, new stars bloomed with renewed vigor, new star clusters like globular clusters formed, and over immense stretches of time, what was once a shapeless, amorphous clump began to distinctly resemble something more familiar, something more structured, something more beautiful. These mergers are a key driver of galactic evolution, shaping their ultimate form and size, driving gas inwards to fuel central black holes, and enriching the interstellar medium with freshly synthesized heavy elements. The grand diversity of galactic forms, a cosmic kaleidoscope of shapes, what ultimately determined the final magnificent shape of a galaxy. That, even today, remains an active and fascinating area of ongoing scientific inquiry, a puzzle we are still diligently trying to solve with sophisticated computer simulations, N-body simulations, hydrodynamical simulations, and large-scale cosmological simulations like illustrious TNG, Eagle, and Romulus, and ever more powerful observational data from telescopes like JWST and the upcoming Vera C. Rubin Observatory. But we do know a few fundamental things that play crucial roles: initial angular momentum, merger history, gas content, the influence of the central supermassive black hole, and environmental effects. Spiral galaxies, the elegant cosmic pinwheels galaxies, that remained relatively undisturbed by major collisions, perhaps experiencing only gentle interactions with smaller neighbors, known as minor mergers, and possessing just the right amount of coherent ordered spin, or angular momentum, could gradually flatten into the elegant, majestic spiral galaxies we admire so much, like our own glorious Milky Way. We, human beings, live tucked comfortably into one of its grand sweeping arms, a tiny suburban speck on the very edge of a vast, slowly rotating cosmic metropolis. Our solar system orbiting its galactic core once every 230 million years. Spiral galaxies are characterized by a flat, rotating disk of stars, gas, and dust, and a central bulge. They tend to retain vast reservoirs of cold gas and dust, the prime ingredients for ongoing star formation. This is why they are often teeming with bright, luminous young blue stars, predominantly found in their spiral arms, lighting up their graceful structures like festive, swirling fairy lights on a grand cosmic scale. The intricate structure of a spiral galaxy is fundamentally all about motion and flow, a dynamic dance of stars and gas in a rotating disk. When a galaxy possesses a moderate amount of angular momentum, meaning its gas and stars are rotating in a somewhat orderly and coordinated way around a central axis, it naturally, inevitably, flattens into a magnificent disk over immense timescales, much like a spinning ball of dough flattening into a pizza under centrifugal force. The cooling of the gas is essential for this flattening process, allowing it to settle into a thin disk. Within that disk, fascinating density waves ripple outwards from the center, like subtle, grand waves in a pond or traffic jams on a highway. These are not waves of physical matter moving, but rather patterns of compression and rarefaction, As gas and stars pass through these density waves, the gas gets compressed, sparking furious bursts of new star formation along the spiral arms. It's important to remember they are not rigid, fixed structures of matter, but rather persistent patterns moving through the galaxy. Individual cars, or stars, move in and out of the jam, but the jam, or the arm, itself persists, a wave of heightened density. Many spiral galaxies also have a central bar-shaped structure, known as a barred spiral galaxy, like the Milky Way is believed to be, and about 2/3 of all spiral galaxies. These bars are elongated structures of stars that rotate as a rigid body and are thought to funnel gas toward the galactic center, fueling star formation there and potentially feeding the central supermassive black hole. The Milky Way, Andromeda, and Triangulum galaxies are prominent examples of spiral galaxies in our local group. The relative prominence of the bulge versus the disk, the bulge-to-disk ratio, in spiral galaxies is an important diagnostic of their merger history, with larger bulges often indicating more significant past mergers. Elliptical galaxies. The serene, ancient giants, of course. Not all galaxies manage to achieve such elegant, ordered beauty and perfect form. Enter the elliptical galaxies, typically older, generally rounder to oval-shaped, and often radiating a sense of being a bit more relaxed, having settled into a stable, less frenetic existence. These galaxies do not possess distinct spiral arms or a prominent disk. Instead, they are more like giant, luminous star clouds, majestically shaped like perfect spheres, or often stretched out into elongated rugby balls or squashed ovals, classified from E0 perfectly spherical to E7 highly elongated based on their apparent eccentricity. They range in size from dwarf ellipticals, much smaller than spirals, to giant ellipticals, which are among the largest galaxies in the universe, often found at the centers of dense galaxy clusters where mergers are more frequent. Elliptical. Galaxies are usually composed predominantly of older, redder, lower mass stars, which have longer lifespans, with very little cold gas or dust remaining to form new ones, giving them a more uniform, often reddish-brown hue. Their star formation rates are typically very low, leading to the term red and dead often used to describe them. If spiral galaxies are the bustling, vibrant, growing cities, then elliptical galaxies are akin to sleepy, well-established retirement communities, quiet, stable, and not particularly prone to sudden changes or new developments. Ellipticals are widely believed to form primarily through dramatic major galactic mergers, especially when two spiral galaxies of similar colossal size collide and intertwine. During such a collision, their previously orderly disk-like motion is profoundly disrupted. The stars are flung into chaotic random orbits like a swarm of bees rather than organized paths in a single plane. The gas within the merging galaxies gets either rapidly used up in a violent burst of star formation or violently blown away by energetic processes like powerful outflows from active galactic nuclei, often powered by the merging supermassive black holes, which can reach luminosities comparable to quasars. The immense energy from these black holes and from the supernovae in the initial starburst can heat the gas to millions of Kelvin, preventing it from cooling and forming new stars, effectively quenching star formation. What is left eventually settles into a massive, more shapeless but ultimately stable spherical or ellipsoidal mass with little net rotation. It's a dramatic, chaotic, and oddly productive process, much like the cosmic version of smashing two beautiful snow globes together and then patiently waiting for the glittery flakes to slowly settle into a new, albeit less organized, configuration. Massive elliptical galaxies often have vast extended halos of hot X-ray emitting gas, the intracluster medium or circumgalactic medium, and a large population of ancient globular clusters, dense spherical collections of hundreds of thousands of stars, often formed during intense merger-induced starbursts, which are remnants of their past merger activity. Irregular galaxies and other forms, the cosmic eclectics. Then there are the fascinating irregular galaxies which, true to their name, don't fit neatly into any conventional category. They are the beautiful oddballs, the delightful nonconformists, the rebels of the cosmic tapestry. They lack a distinct regular shape, often appearing amorphous or clumpy, and typically don't have a clear bulge or disk. Some are relatively young galaxies that simply haven't had sufficient time or opportunity to coalesce into a more defined, symmetrical shape, e.g., dwarf irregulars, which are very common in the early universe and in the present-day universe, often orbiting larger galaxies and exhibiting vigorous ongoing star formation. Others are older galaxies that perhaps ventured a bit too close to a much larger, more massive neighbor, and were gravitationally pulled completely out of alignment, their delicate structures distorted and twisted like a favorite hat blown askew by a powerful gust of wind, e.g. tidally disrupted galaxies or interacting galaxies. Irregular galaxies might appear like haphazard splatters or energetic scribbles of light, but they are often bursting with incredibly intense new star formation, teeming with raw energy and vast potential, often due to the very gravitational disturbances that made them irregular. The compression of gas during close encounters can trigger vigorous starbursts. Examples include the Magellanic Clouds, dwarf galaxies orbiting our Milky Way, which are currently being tidally distorted by our galaxy's gravity and are actively forming stars. Some galaxies naturally fall somewhere between these broad categories: spirals with unusually large central bulges, ellipticals with faint ghostly rings of dust, remnants of swallowed smaller galaxies, and various other hybrid forms, like lenticular galaxies, classified as S0 on the Hubble sequence, which have a prominent disk and bulge, but lack clear spiral arms and have little ongoing star formation, often seen as an intermediate step between spirals and ellipticals, or as faded spirals that have used up or lost their gas. This showcases the endless variety of cosmic evolution. Galaxy classification, much like nearly everything in the vast complex field of astronomy, can be as gloriously messy and intricate as the universe itself, but we still diligently try to categorize them, mainly because that's how us humans, in our inherent quest for understanding, like to make sense of things, even when contemplating the deepest secrets of the stars themselves. It helps us find patterns in the chaos and understand their evolutionary paths, environmental effects, and cosmic downsizing. A galaxy's fate isn't just determined by its internal processes and merger history, its environment plays a huge role. Galaxies. In dense environments like the cores of galaxy clusters, behave very differently from those in the vast empty voids. Mechanisms like ram pressure stripping. As a galaxy moves through the hot, dense intracluster medium, the gas between galaxies in a cluster, this gas can act like a strong headwind, stripping away the galaxy's own cold gas, halting star formation. Tidal stripping. The strong gravitational pull of the cluster as a whole, or of massive central galaxies, can pull stars and dark matter away from individual galaxies. Galaxy harassment. Multiple, rapid, weak gravitational encounters can cumulatively disrupt a galaxy's disk and gas. These environmental effects often lead to galaxies in clusters becoming red and dead ellipticals or lenticulars, while field galaxies, those outside clusters, are more likely to be spirals. Another fascinating aspect of galaxy evolution is cosmic downsizing. This observation shows that the most massive galaxies formed their stars earliest and quickest, while smaller galaxies continued to form stars and grow over a longer period. This is somewhat counterintuitive to the simple hierarchical model, where large galaxies form by accreting smaller ones continuously, and points to the complex interplay of feedback mechanisms, especially from supermassive black holes, that regulated star formation in massive galaxies in the early universe, effectively quenching them at earlier times. Observational evidence and future explorations. The magnificent Hubble Space Telescope, HST, a true marvel of human ingenuity orbiting above Earth's atmosphere, gave us our clearest, most astonishing look at this cosmic diversity for over 3 decades. With its unparalleled vision in visible and ultraviolet light, it has allowed us to observe galaxies in virtually all stages of their vast, incomprehensible lives. From tiny, chaotic proto-galaxies flickering faintly in the earliest universe, albeit with significant redshift, to the majestic, fully formed spirals and massive ellipticals populating the nearby cosmos. We've literally watched galaxies collide in slow-motion ballets of gravity, seen them stretch and tear apart under immense tidal forces, and then, wondrously, observed them rebuilding themselves in the chaotic aftermath, a testament to the universe's self-organizing power and resilience. And now the James Webb Space Telescope, JWST, is pushing the boundaries even further, peering back to an even earlier epoch, revealing galaxies that formed just a few 100 million years after the Big Bang, providing unprecedented details about the very first light and structures. Its unparalleled infrared capabilities allow it to penetrate the dust and gas that often obscure vigorous star formation in distant galaxies, and to observe highly redshifted light from the most distant and ancient galaxies, essentially seeing them as they were when they were very young. The images from JWST are revolutionizing our understanding of early galaxy formation, showing us how quickly massive galaxies and even barred spirals could have formed in the young universe, challenging some previous theoretical models and providing direct evidence for early ionization sources. We are finally starting to see some of the earliest galaxies taking shape, small, chaotic, glowing clumps of stars from just a few 100 million years after the Big Bang, essentially witnessing them in their infancy, their nascent, irregular forms. We are quite literally peering into the very nursery where the first light of structured creation bloomed, witnessing the very dawn of galaxies. Future telescopes and surveys will continue to refine our understanding. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys to map the cosmic web and trace galaxy evolution over cosmic time, especially focusing on dark energy and large-scale structure. Powerful ground-based observatories, like the extremely large telescope ELT, currently under construction in Chile, and the 30-meter telescope TMT, planned for Hawaii, will provide even more detailed spectroscopic observations of distant galaxies, allowing us to measure their compositions, kinematics, star formation rates, and the properties of their supermassive black holes with unprecedented precision. Radio telescopes such as the Square Kilometer Array, SKA, will probe the distribution of neutral hydrogen during the dark ages and reionization, providing complementary views of the universe's early history and directly detecting the faint 21 centimeter signal from neutral hydrogen. These instruments, combined with increasingly sophisticated cosmological simulations, will help us unravel the intricate interplay between dark matter, baryonic matter, black hole growth, and stellar feedback in shaping the galaxies we see today. Each and every galaxy, no matter its form or its story, tells a profound tale, a chapter in the cosmic epic, and sometimes that story is most beautifully written in the silent language of its magnificent shape. So, the next time you gaze upon an image of a galaxy, perhaps a perfect spiral with its luminous blue arms, or a glowing serene elliptical halo, or even a wonderfully messy, energetic clump of stars, know that you are not just looking at a static, pretty picture. You are peering into billions of years of history, a profound ongoing story of gravity and light, of countless stars being born, living their brilliant lives, aging and eventually fading, of vast gas clouds drifting silently for eons, then dramatically colliding and becoming something more, something new, something that sings the universe's endless, evolving song of creation. Sweet dreams, Sleep Enigma. May your slumber be deep, peaceful, and filled with cosmic wonder.